Right, the second part of this evening we're going to do is intrinsic safety. Now, this is not going to be the MOXIE course. I would seriously advise you to do the MOXIE course. I'm not going to do the MOXIE course. I'm not going to go into it. As far as I know, the stuff I'm going to tell you is correct as of now. You need to check that in order to exonerate me legally stuff. Basic principles we have is that we have some environments, many environments in WA, which are explosive. They contain flammable materials such as oil and gas. What we have to do, we need to put instruments in that type of environment, but we have to make sure that our instruments do not cause an explosion. When you go and do the MOXIE course, you learn that there's all sorts of classifications for materials. There's ignition energy classifications, and everything has different classifications depending on how much energy you need to light it. For instance, methane takes 160 microjoules to light it. Ethylene takes 80 microjoules to light it. Hydrogen will light with 20 microjoules. 20 microjoules is a little bit more than rubbing your hands together. So hydrogen will light at the drop of a hat. There's different material classifications. Now the main and most interesting one, the main thing about all of this stuff is, and when you do the MOXIE course you'll do more of this, the main thing about all this stuff is it is as boring as batshit. So I really don't want to go into it too much. There are area classifications. Zone 0 is a dangerous area. Continuous risk of explosion. Zone 1, frequent risk of explosion. And Zone 2, occasional risk of explosion. There is, unfortunately, 3 different ways of classifying this. There's the zone system, the international system. The zone system goes from 0 to 2, with 0 being the most dangerous, 2 being the least dangerous. The international system, which goes from 0 to 2, and then there's the American system. The American system goes from 1 to 3, because they just got to be different. I have heard that the American system will be following the international system. That would be nice. The countable faults, what this means is how many faults have to occur, or how many faults does the piece of equipment have to be able to survive before it's in danger of starting a fire or starting ignition. If you're putting equipment into a zone 0 area, it has to be able to survive 2 faults. If you're into a zone 1 area, it has to be able to survive 1 fault before there's a chance of ignition. To prevent ignition, there's 3 things which you have to have in order to create ignition. You have to have fuel, you have to have an oxidizer, something which provides oxygen, and you have to have an ignition source, something which will provide ignition. Now, those 3 things is what you need. The main way of preventing ignition is to make sure that those 3 things do not come into contact. So the first way is to physically keep those 3 things apart. The second way is to make sure that you never provide enough energy to let ignition occur. So if there isn't enough energy for ignition to occur, then ignition won't occur. So the way, when we're using instrumentation, our main method is going to be to stop the energy occurring, to make sure there's not enough energy to allow ignition. The third method is to say, okay, there will be an explosion, but what we're going to do is we're going to contain it in an explosion-proof case. so that the explosion won't spread to the rest of the world. It will just be contained. So we have three main methods that we use in instrumentation to do instrumentation within a hazardous area. One method is we have uncertified equipment which we connect to normal instrumentation equipment in the hazardous area, and in between the two we have a thing called an intrinsic safety interface. And the job of the intrinsic safety interface is to make sure that there is not enough energy in the hazardous area to cause an explosion. The second method we use is to encase the instrument and all the cabling and the conduit in explosion-proof containers. Steel conduit, closed at both ends, all in explosion-proof containment, so that if there is an explosion within the box, the explosion stays within the box. The third method which we use in instrumentation is that we blow pure air from the safe area into the instrument and the conduit. The thinking is, if air is always coming out of the instrument because the instrument is pressurized, then explosive gas can't get in. So if explosive gas can't get in, there can't be an explosion. So that's the third method. With the third method, we have a couple of problems. We have to have a sensor in. We have to have a sensor there which is proving airflow. And then we have a sensor just in here which is proving that we have pressure. If either of one of those sensors breaks down, we have to power the instrument down. That can make it a quite unreliable instrument, especially with the airflow sensor. It's very hard to detect a small airflow. The pressure sensor is also a pain because that means if you open the door, the whole instrument shuts down. Our main method is then to use intrinsic safety interfaces. The idea of these is to make sure that there is not enough energy to create ignition. Now I've got a question for you. As far as you've got a choice, amps or volts, what creates sparks? Big amps or big volts? Actually, it's volts. Now you should be able to guess that by the fact that if you want a spark plug, if you've got a spark plug and you need to create a spark on a spark plug, what you need is lots of volts. So you have the coil in your car which takes the 12 volts and ups it to 20,000 to get you a spark. So sparks you get if you get lots of volts. Now the other way of creating ignition is like an electric cooker or a cigarette lighter in a car, and that is by heating. If you've got a piece of wire and you want to heat a piece, oh that's the wrong colour, isn't it? If you've got a piece of wire and you want to heat up that piece of wire, what's the important thing, amps or volts? Yep, amps. So sparks are caused by volts, and heating is by amps. We put these barriers, these intrinsic safety interfaces in, and their job is to make sure that there isn't enough volts to spark and there isn't enough amps to heat. We've got two types of intrinsic safety barriers, the Zener barrier and the galvanic barrier. And if we put those in, it means that our instrument should work just fine, but there will never be enough volts to spark, and there will never be enough amps to heat. And that way, it won't be us that causes ignition. First one we'll look at is the Zener barrier. Now, we've got a couple of things in there. The way a Zener barrier works is, it's kind of a reverse fuse, if you like. When the voltage gets high, the Zener barrier's resistance suddenly drops to 0. So that if a high voltage is put on a Zener barrier, then what happens is that voltage gets passed through the Zener barrier straight to earth. So as soon as you put high voltage on a Zener barrier, the Zener barrier shorts out and goes to earth. And when you take that high voltage away, the Zener barrier then opens up again and goes closed circuit. The Zener barriers are designed to be able to protect against 250 volts RMS. That means that you are not allowed to have more than 250 volts RMS within the same cabinet as a Zener diode or Zener barriers. It can't protect, it's not designed to protect against any more than that. So it's designed to, if you put 250 volts on there, or anything more than the voltage you're supposed to put, it just shorts the whole thing to earth and makes it safe. That's how it gets rid of voltage. It gets rid of current using two things, the resistor and the fuse. The resistor that is there to reduce the speed at which current can build up, and the fuse is there to blow. If the current goes too high, the fuse blows. End of chat. So the resistor's there to make sure that you don't get a sudden pulse, because it slows it down, and the fuse will blow. Now, I've got a question for you. As you can see, this circuit shows 3 Zener diodes. Does anybody have any idea why there are 3 Zener diodes? I should say that any one of them would do the job. Why are there 3 of them? Yeah, you're right. It's for safety. See, the problem with the Zener diode is, if you put a high voltage on it, it's supposed to short out. And when you take that high voltage off, it's supposed to go closed circuit again. But what happens is, sometimes they burn out. So every now and then, after you've, for instance, tested it, one of the Zener diodes is dead. And then maybe a little while later you might test the second one, and the second one might not recover. So we have 3 on there for safety, because you're probably going to blow the first one up when you do install and you test it the first time. You're probably going to blow the second one up the next time it gets used, which leaves you 1 as a fallback. So that is one problem with Zener diodes. You can even be in a situation where you don't have any diodes working, and then you're in strife, because the 250 volts, if it shorts onto that contact, will go straight through, and we have got a problem. Another big problem with Zener diodes is they have to be very, very, very well earthed. They have to have their own dedicated conductor back to the reference ground, which may mean the earth spike. Their own dedicated conductor. It has to be 4 mm minimum, and it has to have a maximum of 1 ohm. They have to have a very good earth. The device itself cannot be earthed. The device has to be floated. So the device which is over here, this device is sitting, it's not earthed reference to its case. The device is not connected to its casing. The casing needs to be earthed back to the structural ground, but the device not earthed to the casing. This leads to a few other little problems. It leads to a thing called common mode rejection. Basically, it picks up noise. It picks up mobile phones, it picks up fluoros, it picks up noisy two-ways, it picks up every piece of noise that's floating around. So it tends to make for a very noisy signal. In its favour though, it's very cheap, it's very simple, and it's reasonably reliable, and it's been around forever. So that's the reason why we use Zener barriers. They're cheap and we've always used them. Instrument people tend to be a very conservative bunch. They don't like new things. So we've always used Zeners. We've used them for 20, 30 odd years. There is another alternative, and that's a thing called a galvanic isolator. A galvanic barrier uses things like transformers and relays and little things called opto-isolators to make sure that there's no connection between the power side of the instrument and the instrument side of the instrument, to make sure that there just will not be enough volts to spark and there will not be enough current to heat. So it uses these galvanic isolation methods. It is more expensive. It's a more expensive isolation method. You do not get the common mode problems. It doesn't pick up noise. In fact, using transformers and opto-isolators is a really effective way of getting rid of the noise. So the galvanic isolators are much better at getting rid of noise. They are more reliable. They won't blow up when you test them. On the downside, they're new. They're newish anyway. And they are more expensive. I'll just see if I can... There's a picture of a typical galvanic isolator. They are more expensive. I know a lot of places now where they have an active policy. They go in and every time they have a shutdown, they change 5 of the Zeners for 5 galvanics. Just because it gives them a better sense of security. And, you know, if they were scheduled to test the damn things anyway, they probably would have ended up blowing. Price difference. If you just bear with me. Okay, to give you an idea of the price difference, I've just looked it up on the web, and Zener diodes, you can get them from anything from $50 to $200. Galvanic isolators, quote, on application. So they might be a bit more. I honestly, I should have the prices, but I don't. So it looks like the galvanics are more expensive, but they're well worth getting because of the difference in reliability.